Welcome to Lecture 22. I don't know about you, but I'm excited. Two more to go, and the last one will be fairly short. What we talked about at the end of Lecture 21 was that pertains to what we're about to talk about was the kinetic molecular theory, and we went over four postulates. One, gas particles are far apart. Okay, which allows for them to be compressible and so on, and also to not exert any attractive forces. So no attractive forces on our ideal gas that obeys the laws we're going to talk about today. Speed proportional to temperature. And I might have to peek for the fourth one. There's a fourth postulate. The other thing we talked about was pressure. Pressure, in terms of a gas, is the particles hitting the sides of a container. Of course, if the temperature goes up, the pressure goes up because the particles will move faster and hit the container more often. If you increase the size of the container, so now the particles have farther to go, then the pressure will go down, and conversely it will increase if you decrease the volume. If you increase the number of particles, you will increase the pressure. So four variables that we came up with that must be taken into account when we are dealing with gases is pressure, volume, amount, and we'll be dealing with that in moles, of course, and temperature, and we must use the Kelvin scale. So we're going to look at the relationship between these variables today as we talk about the simple gas laws, Dalton's law of partial pressures, essentially you add them up, and how much does 1 mole of a gas occupy, our last addition to the mole chart. So let's scroll up to the previous lecture and see what that fourth postulate was that I cannot remember right off the top of my head. I have them in bold in the notes. Far apart, collisions are elastic. So when they collide, they don't lose any energy. Of course, in the real world, this is not necessarily the case. If there are attractive forces, and for some gases, they are attracted to one another. For instance, hydrogen chloride. Hydrogen chloride is a gas. If you dissolve it in water, now you've made hydrochloric acid because you make all these hydronium ions and chloride ions. But hydrogen chloride, pure hydrogen chloride, is a gas. Those particles, that's a polar bond. Now, chlorine has a higher electronegativity than hydrogen, so you get a little partial negative at this end and a partial positive at this end. There are attractive forces between them. Otherwise, hydrogen chloride would not dissolve in in water, sorry. Ammonia was the next example I was going to talk about. Ammonia, because of its geometry and the fact that nitrogen has a higher electronegativity than hydrogen, it is also a polar molecule. Negative in where the nitrogen is, it's trigonal pyramidal in its geometry, and a positive end where those hydrogens are. Oops. A negative and a positive, not two positives. It also is a polar gas, and it dissolves in water to produce ammonium and hydroxide. So these two, this acid and this base, and that's a weak base, are polar gases. So of course they have attractive forces and will certainly not obey the four postulates of the kinetic molecular theory. But we're going to look at those four basic variables and how in an ideal world they would be related to one another. Of course, if pressure goes up, volume should be going down for these two gases as well. It's just they won't obey the laws exactly mathematically. All right, so let's get on with those gas laws. What we're going to do first is compare two variables at a time. And we're going to go all the way back to the 1600s to Robert Boyle, Boyle's law. For each of these first three laws, only two variables are considered, And that means that the other two that are not being compared in the gas law that we're talking about are held constant. So if we're looking at pressure and volume, then that means temperature and amount are constant. So what Boyle found out in doing experiments was that as the pressure goes up, the volume goes down. These two variables are inversely proportional. So pressure and volume are inversely proportional. And those are the only two out of the four that are inversely proportional. As one goes up, the other one goes down. So let's look at this little video just so I can kind of show you Boyle's law in action. Just to spice things up a little bit. Oops, sorry. Oh no. All right. I like the music. It wasn't that dramatic of a video, but sure beats the experiment I used to do with my high school students, and that was putting bricks on top of a closed syringe. The bricks being more pressure, and that would make the syringe decrease in volume. Yeah, I think that video is a little more exciting than that. Okay, so inversely proportional. Your units we don't have to worry about units here. The two pressures just need to be in the same units. So it's very much like the M1 V1 equals M2 V2, okay? You are making a change. You only have pressure and volume. Pressure can be in any units as long as the two sides are the same, and volume can be in any units as long as the two sides are the same. All right? So we will do some practice problems using Boyle's law. The next one to talk about is Charles' law. And notice that these two right here look very different from Boyle's law. So I'll write it up here. The two variables that are inversely proportional to one another are in an equation like this. Because if I said P1 V1 equals a constant, okay, then P1 equals constant divided by V1, and therefore they are, one goes up, one goes down. In volume and temperature, okay, They are directly proportional, so, or pressure and temperature, so directly proportional. See how the equations look different? So these two variables are directly proportional, and so are these two. The two equations look exactly the same. And in fact, there's another one, because we haven't dealt with amount yet, and that's Avogadro's law, and it looks, as it relates to volume, and it looks just like these. So if I took V1 T1 equals a constant, then V1, boop, my bad. That is not how the equation looks. So V1 over T1 is equal to a constant. So V1 is equal to the constant times T1. Now what is this constant business? Well, of course, you are dealing with volume and temperature. The units are completely different. So this constant would be what we call a proportionality constant to take care of the difference in units. So you see that volume and temperature are basically, you know, one goes up, the other one goes up. Over here, if this goes up, then this must go down, volume. All right, same thing is going to be true with Gay-Lussac's law. So I found two other exciting videos to watch to show these two variables in action. Pretty cool, right? You can watch others. You know how to do it. All right, so volume and temperature directly proportional. Putting those balloons into liquid nitrogen, and I've done that as a demo myself, and that liquid nitrogen is about minus 200 degrees Celsius, so it's very, very cold. Anyway, as you put it into the very cold liquid nitrogen, the volume decreases. You are slowing those particles down so much that they don't need as much room, and therefore the volume decreases. We can show exactly the same thing with temperature and pressure. You slow the particles down by cooling them, by slowing them down by cooling them down, then they are going to hit the sides of the container less often, decreasing the pressure. So once again, these are directly proportional since it looks exactly like Charles' law. This is Gay-Lussac's law. So in the case of Charles' law, we were dealing with volume and temperature, so therefore amount and pressure are constant. You don't have any information about those. And in Gay-Lussac's law, volume and amount are constant. All right, and in just a minute after we watch one more exciting video, we're going to put those three laws together into what's called the combined gas law. So let's watch one more video on these gases.
This video is about a real-life application of Gay-Lussac's as well. As the law states, the pressure and temperature of a gas are directly related. As you can see here, I have a tin can filled with a small amount of water that I've brought to a boil. The pressure inside of the can is far greater than the pressure outside of the can. Pressure inside of the can is greater because some of the water being boiled has turned into water vapor, causing an increase in pressure. I'm going to put the can inside this tub of ice water. Being in the tub of ice water, the can will rapidly cool. Along with the rapid cooling of the water, the pressure will decrease as well. The pressure will decrease so low it will be lower than the pressure inside of the can will be lower than the pressure outside the can, causing the can to collapse on itself. Let's see it in action. Oh my God, that worked. Got it. So, this is the result of the crushed can. Alright.
Obviously, some people had to do videos for an assignment. Good job, guys. All right, so pressure and temperature directly proportional. For those of you who have never lived up north, you don't realize that in the winter, you actually have to put more air in your tires because the pressure decreases when it gets really cold outside. I remember one Christmas Eve, my husband and I were living in New Jersey, and it was 10 degrees outside, and we had to stop and put air in our tires. Wasn't me that got out of the car. All right. And then on a hot summer day, you can actually, your pressure in your tires is higher. Combined gas law takes Boyle's law, Charles' law, and Gay-Lussac's law and combines them together so that the only thing you're holding constant is amount. Okay? So, where are those laws? There's Boyle's law, here's Charles' law, and pressure and temperature here is Gay-Lussac's law. So it's just combining the three so you can change three variables at one time. Craziness. All right. All right, Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressures. All right, so where are we most familiar with a mixture of gases? In our own atmosphere. Notice that the word mixture, this law does not apply to cases where gases react in a chemical reaction. So and I'll read, we'll go over the rest of this in just a moment. In our atmosphere, we have about 70% nitrogen. Okay. You have a recitation problem similar to this. You have about 20% oxygen. And then you got a whole bunch of other stuff. You got some CO2, you got a little helium, you got a little bit of everything. So the pressure of nitrogen, of course, is going to be affected by the fact that nitrogen weighs 28 grams per mole, and the particles are a certain size. Oxygen weighs 32. Carbon dioxide weighs 44, helium weighs 4. So the pressures of each of these gases is dependent only upon the molecules that make up that gas. So if I look at atmospheric pressure, 70% of the atmospheric pressure is due to nitrogen, and 20% to oxygen, and so on. So these partial pressures are written as lowercase p's. So in the atmosphere, the pressure of nitrogen plus the pressure due to oxygen, plus the pressure due to carbon dioxide, and so on, okay, plus ... equals the total pressure, which on any given day, changes. Here, where we live at sea level, it's about 1 atmosphere. So the sum of the partial pressures is the total pressure, and that really is all there is to Dalton's law of partial pressures. Now, one application of Dalton's law of partial pressures is the fact that one of the gases that's in here is water. We often have a lot of water vapor in the air, and we call that humidity. All right, so which season has more water vapor in the air, summer or winter? Well, this year it'd be hard to say. The original thinking about gases and how they combined with one another was something like this, according to Dalton. So we didn't know that nitrogen was N2 and hydrogen was H2 and ammonia was in H3. There was no idea that gases existed as molecules until Gay-Lussac and Avogadro sorted some things out. So there's Gay-Lussac's law, okay, and so on. So he also said that, and this is important for our last lecture because we're going to apply it. So here's a chemical reaction. So one thing that he observed was this, that gaseous reactants and products can be expressed as ratios of small whole numbers. Well, this looks really familiar because we use this we revisit this ammonia equation a lot. So what it turns out is, remember those coefficients in chemical reactions being either particles or moles? Well, they can also be, let me scroll back up. We're going to both on the same page. There we go. They can also be volumes if you're talking about gases. So 1 liter of nitrogen, 1 nitrogen in the equation. 3 liters of hydrogen, 3 moles of hydrogen. 2 liters of ammonia, 2 moles of ammonia. So if you are using gases, you can relate their coefficients in volume. So what it means is this. If I had half a liter of nitrogen, and under the same conditions, I wanted to know how much ammonia, oops, right, put the unit, how many liters of ammonia would you make? Don't have to go through the mole and everything. All I have to do is say 0.5 liters times mole ratio, in this case volume ratio, times 2 over 1, because I'm going from nitrogen to ammonia, okay? So 1 liter of ammonia. This is only true for gases. All right, so the volume relationship was the same as the coefficients we have been using. All right. So the only way the volumes can be the same as the coefficients is if equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Because you know how the mole contains equal numbers of molecules? So volumes at the same temperature and pressure of gases also contain the same number of molecules. All right, Avogadro's law also shows that the relationship between volume and the amount of gas is directly proportional. Okay, so volume equals a constant times N. So once again, we have that directly proportional like equation that we had with both Charles' law and Gay-Lussac's law. Now, one more thing. So one more take home from Avogadro is that 1 mole of any gas at standard temperature and pressure, 0 degrees Celsius, 1 atmosphere pressure, occupies the same volume, therefore has the same number of particles, 22.4 liters. So we know that 1 mole of anything has the same number of particles. Well, 1 mole of a gas, because it has the same number of particles, occupies this same volume, and we call this the molar volume of a gas. So now we have a complete mole chart, right? So before I leave this page, coefficients can be volumes, can be interpreted as volumes for gases. For gases under same conditions. Okay, so that's one thing we have learned here. Oops. Okay. The other thing we learned is that amount in moles and volume are directly proportional, just like Charles' law, Gay-Lussac's law, and that 1 mole of any gas, and it has to be standard temperature and pressure, occupies the same volume. And we call that the molar volume. So, drum roll please, our mole chart is now complete. So we have our familiar from way back first test that we can go back and forth between moles and mass using the periodic table, molar mass. We can go back and forth between moles and particles using Avogadro's number. We can go back and forth between molarity and moles using the volume. And we can go back and forth between moles and volume of a gas at ATP, STP, using the 22.4 liters per mole. So I would multiply in this direction and divide by it in the other direction. So if I had 5 liters and I wanted to know how many moles is it, yes, we are going to do stoichiometry. Then all I have to do is say 5 liters times 1 mole. It's 22.4. So I divide by the molar volume. So now we're going to put these simple gas laws, Dalton's law of partial pressure, and the molar volume of a gas into practice. All right, this first question. The oxygen emitted from an aquatic plant is collected over water. Total pressure is equal to 753 torr. What is the partial pressure? So we have two gases here. This is Dalton's law of partial pressures. That kind of was the giveaway there. We have pressure of oxygen and pressure of the water. Okay, so water vapor in the air. This is a very common technique. You take a flask like this description here. You got a plant here, okay, and it's producing oxygen due to photosynthesis, little bubble bubble. And what you do is you stick a test tube down into the flask, inverted, filled with water. And then as the oxygen bubbles up into the test tube, the water comes out. Call it collecting gas over water. Well, inside of this test tube is not only the oxygen from the plant, but also the water vapor from the water. Okay, and the two added together is the total pressure. So how do I get this? See table below. We know that humidity is temperature dependent, right? So there's our little water vapor pressure table. And what temperature was it? Sorry. 25 degrees. All right. So at 25 degrees Celsius, we have a vapor pressure of 23.756, and our pressure unit here is torr. 23.756 torr is our water vapor pressure. All right, so before I forget it, the pressure of the water is 23.756 torr. All right, the total pressure is 753. So all I need to do is subtract off the 23.756 to get the pressure of the oxygen. Because remember that total pressure is the two added together. All right, so I'm just going to subtract off the water from both sides. $753 minus 23.756, and I end up with something that, 729.24. 729.24 is my oxygen pressure. So pressure of oxygen is 729.24. All right, so anytime you need to use Dalton's law of partial pressures, you're going to add them up. They add up to the total pressure. All right, scrolling. Let me give myself a little room here. And then a little more room here. All right, and then there if you missed it before. All right, a scuba diver with a lung capacity of 5.2 inhales at a depth of 45 and a pressure. So I have a pressure and a volume. I believe the 45 meters is pretty immaterial. If the diver were to ascend to the surface where the pressure is 1 atmosphere while holding her breath, how much would her lungs have to expand? So you're decreasing the pressure, and this is why you don't hold your breath when you're coming up from a dive. Not that I would know that. I would never be diving. So we're doing pressure and volume, Boyle's law. So P1 V1 equals P2 V2. All right. Pressure 1 is 5.5 atmospheres. Volume 1 is 5.2 liters equals 1 atmosphere times V of V2. Okay, so solving for V2, think you can already see this is going to be a huge number. 5.5 times 5.2. 28.6 liters, because I divide by 1, right? And when I take the 1 atmosphere over here, the atmospheres cancel, and I end up with, what did I say? 28.6 liters. Can your lungs expand to 28.6 liters? I don't think so. So this is how lungs can burst if you're not careful as you're coming up from a dive. All right. Oh, I just love these complete the tables. So it looks like Boyle's law to me. We've got pressures and volumes. All right, so this would be a good time for you to, switch the video off and give these a try. The only thing you need to check is that things are in the same unit. So I've got 2 volumes here in this first one, and they're both in liters. When I solve for P1, my pressure will be in atmospheres, because this pressure right here is in atmospheres. And both pressures in millimeters of mercury. So when I solve this one, my volume will be in milliliters like this. So that's the only thing to check, to make sure that things are in the right units and it looks good. So I'm going to go ahead and start working these. And Boyle's law, P1 V1 equals P2 V2. So solving this first one for P1, solving the second example for V2, and so on. Okay, so I'm just going to start plugging these into my calculator as soon as I turn the lights on, so I can see. All right. So for this first row, I'm going to take P2 times V2. And divide by V1. And I get 2.4 atmospheres. All right. For the second one, I am going to take P1 and V1 and multiply, because they're on the same side, and divide by 709. And I end up with 125.7 or 126 milliliters. So does that make sense? Little increase in pressure, decrease in pressure, small increase in volume. Not a very big change here. All right, the third one, we're going to multiply P1 and V1. And divide by 49.8. And I get 0.373 atmospheres. Okay. So does that make sense? We increased the volume quite a bit, so we decreased the pressure. All right. And for our last one, we are going to multiply P2 and V2. And divide by P1. And I get 17.5 liters. So we increased so here we're at a higher pressure, with this volume. Here we're at a lower pressure, so greater volume. All right, makes sense. All right, so just a lot of Boyle's law calculations. All right, number 4, a syringe containing 1.55 mils volume, and I see 2 temperatures, and they want to know the final volume. So that'll be V2, and we are using, yes, you guessed it, Charles' law. Now, before we can plug in, we need to change these temperatures to Kelvin. All temperatures must be in Kelvin. So I'm going to add 273.15 to both. So that will make this, which is T2, 273.15, because I'm adding it to 0, 95.3 plus 273.15, I'm going to end up with 368.45, and that's my T1. Okay, so plugging in V1, 1.55 mils. Now we are solving for V2, all right? So I'll be taking T2 to the other side, so it'll actually end up being here because I'm multiplying both sides by T2, okay? All right, so 1.55 mils times T2, 273.15. I'm going to do a little erasing here, okay, so we're not confused. So times 273.15 divided by the T1, okay, which is 368.45. And that will equal V2. Another way to do it would be we could have done it would be to cross multiply and divide, okay, we would have gotten the same result. So 273.15 times 1.55 divided by 368.45. And we end up with 1.15 as our V2. And it's always good to look at what you got and see if it makes sense, okay? And that's milliliters. So we cooled, and these are directly proportional, so the volume should have decreased, and it did. Alrighty, scrolling. And that is going to end our lecture for today. I'm really thinking that I ought to combine these last two and just make it one lecture and be done with it. All right, so number 5, let me scroll just a little bit more before we get started. A cylinder with a movable piston contains 218, so I've got a volume and a pressure and a temperature. They want to know the final volume, and it looks like we're changing 3 things at a time. So I'm thinking I'd combine a gas law. Now, when you have this many things to deal with, I think it is much easier to move things around while you just have the letter, the variables. So we're looking for final volume, so that is V2. So it's on top, that's good, that makes things easier. So I'm going to do it over here, P1, V1, T2, because I'd be multiplying both sides by T2, over T1 times P2, because I would be dividing by P2 on both sides, right? Okay, so erasing. Equals V2. My temperatures are already in Kelvin, so that's nice. Yes, they are. All right, so P1 is 1.32 atmospheres. V1 is 218 milliliters. And T2 is 335 Kelvin. All right, divided by T1, 298 K, times P2, 1.55 atmospheres. All right, so atmospheres cancel, and K's cancel, and I end up with milliliters. All right, I just did my denominator, stored it. And then my numerator divided by, and I end up with 208.7 milliliters. And when you're changing 3 things at a time, it's kind of difficult to check. I'm going to redo the numbers one more time. Okay. I get the same answer, 208.7 milliliters. All right. Number 6, calculate the volume of each gas sample at STP. So we're at standard temperature and pressure. So we are going to use that completed mole chart where we are going, and I'm going to do it down here at the bottom, where we're going from moles, which is what we're given in this problem, to volume for a gas. And we are going to be using moles times 22.4 times liters per mole. So when I take those moles, I'll be multiplying times 22.4. Does it matter what the formulas are? No, not as long as I'm in moles. All right, now if they'd given you grams and you had to switch to moles, then it would have mattered what the formula was. But they didn't do that, so this is actually pretty repetitive, and we're just going to use the molar volume relationship. Okay, so 21.2. And you can only do this if you're at standard temperature and pressure. And I end up with 474.9 for A, liters. And 4.82 liters for B. .15 liters for C. And 192.6 liters for D. So what have we done here in the practice? We have done a molar volume for number 6, combined gas law for number 5. We did Charles' law for number 4. 2 and 3 used Boyle's law. And number 1 used the Dalton's law of partial pressures. The only one we did not use was Gay-Lussac's law. And I will start the next lecture doing an example using Gay-Lussac's law. And what I'm going to do is I'm going to pause, go find an example for that, and I'm going to start then with lecture 23, and that's one less lecture. You have to, well, you know what? We're at 42 minutes. I'm going to pause, go find a Gay-Lussac's question, and I will stop it here, and we'll finish lecture 23 as a separate lecture. So, change. All right, I realized we did not have an Avogadro's law question either, so I added one of those as well. All right, hopefully if you got the notes before I made these changes, then you can add these quickly. If you didn't get the notes until after I changed them, then no problem. All right, number 7, we have a moles, so that's amount, and we have a volume. So we are going to be using, they want to know the new volume. So we are going to be using Avogadro's law, which states that the moles and the volume are directly proportional in this type of equation. So 0.48, and we are looking for the new volume. Now, that is here. So before I start putting my numbers in, let's rearrange that equation. Let's cross multiply. So N1 V2 equals N2 V1. I am looking for this. So I'm going to be dividing both sides by N1. So my V2 is equal to N2 V1 over N1. Okay, a little more erasing. Alrighty, so now let's plug our numbers in. Wait, I left something out, sorry. Occupies the volume. What is the volume of 0.72 moles? I'll get it back. Okay, under the same conditions. So the conditions are that the temperature and the pressure did not change. All right, so now we got it. So 0.72 moles times 11.7 liters divided by N1, which was the 0.48 moles. So amount and volume, and they're directly proportional. So 0.72 times 11.7, and then divide that by 0.48. So our amount went up and our volume did as well. So 17.6 liters. All right, so Avogadro's law. Number 8, I had to make up a Gay-Lussac's law. I did not find one, in your textbook. So I borrowed from the video. So we had a Coke can with lots of water vapor in it, which has a higher pressure than the pressure outside of it. Is cooled rapidly from 100 to 0 degrees Celsius. What will the new pressure be inside the can? So it's P1 over T1 equals P2 over T2. We are looking for P2, so we'll be multiplying both sides by T2. All right, so putting our variables in, that's T2, look like an equal sign. Change must have temperatures in Kelvin, so plus the 273.15. So this is T1 and it's 373.15, and T2 is 0, so plus the same thing. And this is our T2. Okay, so 273.15 times P1, 2.4 atmospheres, divided by T1, which was 373.15. Okay? And our new pressure, temperature went down, so pressure should go down, and it did. 1.76 atmospheres is our new pressure. And that concludes lecture 22. One more to go.